Good evening, everyone. Welcome to the 11th episode of Nodutalk. In today's topic, we are going to cover how to calculate the modulus, then method of risering, type of risers, bottle risers, riserless design, directly applied risering, and we can go through one of the calculations, how to calculate the riser size and neck area. Over to you, Dr. Baswekar.
Good afternoon, people. We'll just go through these contents, objectives, and essential components of risering, observations, how to calculate modulus. Modulus is a concept on which the whole risering system is based. Mold quality, peculiar to SG iron, liquid iron processing of SG iron, risering methods, and then types of methods used for calculating the risers. The objective of risering is to produce castings without shrinkage defects. That's the main object. That's why we are in the business. Then economic production. We have to maximize the casting yield. The normal casting yield is around 45 to 50% in dieselmatic, and in steel casting it can be around maybe 50%, and in SGI it can go up to 70%, 72%, 75%. It is possible. So let us see how we can achieve some of these values to improve the casting yield without compromising on the quality. The essential components of riser design is first the risers. Preferably we use blind risers. Blind means the risers are close to the top. They are close at the top. They are not open to the atmosphere. That's what we call by blind risers. In the riser contact, the connection between the riser and the casting should be as short as possible. Then the design. Dimensions of the risering design are measured at the notch. The notch is the point at which we cause to break the riser when we are separating the riser from the casting during the fettling operation. So the dimensions to be measured at the notch, which is provided at the riser neck. Gate. The ingates in the SGI casting when you are doing riser design have to be thin and wide. For fast freezing, we want to isolate after pouring is over. We want to isolate the running system from the casting and the riser. So the only connection is the gates. So we want to freeze the gates immediately after the pouring is over, so that the casting and the riser design are separated to see how the riser feeds the casting and produces a shrinkage-free defectless casting. Vents, these are provided in the mold to assist the fast mold filling, because a lot of mold gases. Vents have to be provided to assist fast mold filling for providing escape path for the mold gases. So these are the essential components: riser blind, riser contact as short as possible, design dimensions to be measured at the notch, gates should be wide and thin for fast freezing, and vents to help in reducing the back pressure of the mold gases during the pouring operation, so that the mold can be filled fast. So vents are to reduce the back pressure of the mold gases. In SG iron, volume changes on cooling and solidifying cast irons, and this volume change results in net volume increase of iron in the mold. The density of liquid metal, as you know, is about 6.9 to 7, and it's got about 3 to maybe 4% carbon. Carbon has a density lower than that of liquid iron. So when the carbon comes out from the liquid metal during the solidification process, it occupies more volume. So there is a volume change as the cooling takes place. When you pour the mold, the metal is at high temperature. As the metal cools, the metal contracts. As the solidification starts, the metal volume increases because the graphite is coming out. So there is a net increase volume in the mold cavity. And the net volume increase can produce liquid pressure on the mold walls of about 2 megapascals. Now, this pressure normally exceeds the elastic limit of the mold material, except for very, very rigid molds, just like for example, metal molds. So the pressure exceeds the elastic limit of the mold material, leading to mold enlargement and swollen castings. And often these swollen castings contain shrinkage defects inside. Greens and molds are not rigid for this purpose in AGIN, quite weak molds. So we have to use techniques to control the mold wall expansion and to get shrinkage-free casting. So volume changes in SGIN due to presence of graphite. Net volume increases and produces pressure on the mold. The pressure is normally more than the elastic limit of the mold material, and this causes mold enlargement or oversized casting, and these castings mostly contain some defects inside, shrinkage defects inside. Now, riser functioning is very sensitive to pouring temperature and pouring time. So now this brings into the limelight all the important parameters that we consider during the processing of SGI. So riser functioning is very sensitive to pouring temperature and pouring time. The volume change pattern is not constant, but varies according to the cooling rate and condition of the liquid metal, which depends on the processing route. For example, the superheat or the charge composition and melting method, inoculation, etc. These and other parameters affect the volume change. So although you may be using the same pattern all the time, your processing may not be the same all the time the same. And therefore, the volume changes sometimes gives you shrinkage in the casting, and you are wondering what happened. I have not changed the gating system. I have not changed the process. I have not changed anything. How did this happen? Something has gone wrong in the other factors which affect the volume change pattern of the SGN casting. Keep this in mind. The processing change should be as constant as possible. Process control. Molds must be clamped firmly to withstand this pressure during pouring and solidification. Weighting or putting counterweights alone may not be sufficient. So just by putting counterweights, one may not be able to withstand the extremely high pressure on the mold, which is generated when the solidification starts in the mold cavity with the metal. You are going to hear this word again and again, the modulus of the riser, the modulus of the neck. These are the parameters which will help us in designing the risers. For example, modulus is defined as the total volume of the casting divided by the total cooling surface area of the casting. You see the formula given for modulus at the bottom. Volume of the casting, total volume of the casting divided by the total cooling surface area of the casting. We'll go through the diagram on the slide given. A casting is shown at the bottom with the shrinkage cavity, and when the casting has got complex shapes, we divide the casting section into simple shapes, squares, rectangulars, circles, and so on and so forth. Now, the general formula for the modulus is the volume of the casting divided by the surface area. So volume is normally expressed in length cube, and the surface area is expressed in length square. So length cube divided by length square leaves you length. So the modulus always expressed in centimeters, inches, millimeters in the length parameter. So here we have done the calculations of the section 1, 2, and 3 into which this casting at the bottom has been divided. The casting at the bottom has been divided in simple sections, and using this formula, in the formula A and B are the sides of the risers, and C is a non-cooling surface or non-cooling side of the casting. Now in figure you can see A and B and C. So the modulus of the casting is 5 multiplied by 2.5, which is the sides, and divided by the 2A plus B minus C, and this gives you a modulus of 1 centimeter. Similarly, you have the modulus of the section 2, which is 1.5 millimeters. And similarly, we have the modulus of section 3, which is 1.8 millimeters. Now, the sections having the highest modulus is what we call the significant modulus. And the riser is normally attached to the significant modulus or the biggest section where the shrinkage is most likely to take place. So, modulus is required to identify the largest modulus of the casting where we have to attach the riser. Now, if the casting has got different sections, some big sections, some small sections, some large sections, some thin sections, then we have to find the modulus of all these sections and attach the riser to the largest section. If the largest sections are separated by the thin section, you have to apply or connect the riser to the other section modulus. So, if the sections are having different modulus, you have to attach the riser to the first significant modulus section, and then to the next significant modulus section, and next to the third significant modulus section. In casting section changes, we have to apply the riser or connect the riser to every significant modulus section. Let us see what is known as the mold quality. Our objective is to avoid enlargement of the mold due to high liquid pressure exerted by the cooling and solidifying graphitic iron. Green sand and shell molds will not withstand the solidification pressure. Chemically bonded sand molds will resist the solidification pressure if they are properly prepared. By properly prepared, we mean mechanical compaction of the sand during mold preparation and adequate curing of the mold. Cement sand, CO2 or silicate sand, dry sand molds will normally withstand the pressure of the iron solidification. So objective is to avoid mold enlargement. Green sand and shell sand molds are not strong enough to withstand the solidification pressure. Chemically sand will resist the pressure if they are prepared properly using mechanical compaction. And cement sand, silicate sand, dry sand are normally strong enough to withstand the solidification pressure. Some factors which increase the shrinkage tendency of SG iron. These factors are high melt superheat. If we unnecessarily superheat the metal becomes more shrinkage prone. It increases shrinkage tendency of the unnecessarily superheated iron metal. Holding the metal in the furnace for long holding times of the metal in the furnace increases the shrinkage tendency of the SG iron based metal. High proportion of foundry returns scrap or steel scrap in the charge makeup. If you use too much of foundry returns or steel scrap in the charge, you have a tendency of iron not being more shrinkage tendency. So to reduce the foundry's return, we use more efficient risering method so that the yield improves. Presence of carbide stabilizing elements in the melt chemistry. This includes the magnesium which we introduce in the metal through the magnesium treatment. So magnesium is a very strong carbide former. So presence of carbide stabilizing elements, chromium, magnesium, vanadium, so on and so forth, will increase the shrinkage tendency of the metal. Improper carbon equivalent. We have seen in one of the talks how the carbon equivalent is selected depending upon the cooling rate of the casting and the size of the casting. Improper carbon equivalent of the metal means improper carbon and silicon content of the metal will affect the volume changes in the risers and the casting, which will or can lead to shrinkage in the casting. Inadequate inoculation. If the inoculation is not proper, if there are any carbides in the casting, you can be sure that casting is not of good metal quality. So high metal superheat, unnecessarily metal holding in the furnace for long holding times, high proportion of foundry returns, scrap or steel scrap in the charge makeup, presence of carbide stabilizing elements in the chemistry, including high magnesium residual elements left after the magnesium treatment, improper carbon equivalent of the iron. Please remember that the carbon and silicon shown by the spectrometer are not quite so accurate as far as the carbon equivalent calculations are concerned. We take them very approximate values. The carbon is best determined by the carbon sulfur analyzer. And inadequate inoculation. We have seen in the earlier lectures the role of inoculation, like post inoculation, days inoculation, steam inoculation, mold inoculation. These are all part of iron processing, which contribute to reducing the shrinkage in the casting. The combined effect of these process variables can be determined very approximately by measuring the nodal count on the standard test bar. Nodal count increases with the faster cooling. We know this thing. In thin wall casting, we see high nodal count. In average wall casting, we see little lower nodal count. And very large section casting, we see nodal count as low as 20, 25. And in the fast cooling casting, thin wall casting, we can get nodal counts of even 350, 400 and more. So combined effect of these process variables can be assessed by approximately measuring the nodal count on the standard test bar. Standard test bar, for example, could be a Y block, which we use for getting the tensile strength sample cut and polished and machined from the Y block, keel blocks or Y block. So that can be used as a standard test piece to assess the nodal count after the last mold is poured to get an idea about the cooling rate or the of these castings. Ions that show low tendency to shrinkage have low tendency to form as-cast carbide. If you see as-cast carbides in the microstructure, you can be sure that your iron is having high shrinkage tendency. So ions that show low tendency to shrinkage have low tendency to form iron carbide or as-cast carbide. Such ions which do not have shrinkage and have a low tendency for forming carbides, these ions are known as good quality, metallurgical quality ions. Such ions are said to possess good metallurgical quality. We can produce more efficient risers, high yield, if we have the castings made out of metal which is processed to good metallurgical quality. So good metallurgical quality iron preparation is part of the process control to enable increase of the riser yield. The presence of any types of carbides in the ASCA structure should be considered as an indication that the iron has poor metallurgical quality. Subsequently, problems with shrinkage defects can be expected in the cast. So, combining effect of process variables is to get an approximate idea of the nodule count in the standard test bar. Irons will show low tendency to shrinkage if they have got good metallurgical quality, and presence of any carbides is a forewarning that your iron has got poor metallurgical quality. The risering liquid metal iron processing methods. Risering methods take advantage of the fact that graphite cast iron expands during cooling, unlike steel or white iron or malleable iron. Malleable iron is basically white iron after heat treatment converted to malleable iron. So unlike steels and white irons, risering methods take advantage of the fact that graphite cast iron, gray iron and SG iron expand during cooling and solidification. Weak molds, green sand, shell molds, non-compacted chemically bonded sand, these are all producing weak molds which cannot withstand the solidification pressure of the expanding liquid. Strong molds are well compacted chemically bonded sand molds, cement sand molds, CO2 or silicate sand molds, dry sand molds properly clamped, and permanent molds properly clamped. These are strong molds. There are three basic methods of risering. Actually, using the principle which I just outlined below, above, pressure control risering. We use the pressure of the expanding metal to design a riser which will be a very efficient riser. Bottled riser is one of the two methods of designing the riser under the pressure control risering. We control the pressure during solidification and during cooling of the mold or the metal in the mold after pouring to take care of the shrinkage cavity. The next method is a directly applied risering, and the third method is riserless casting. You make the casting almost with zero riser with the use of chills or with the help of cooling aids or using a very, very, very small riser. So pressure control risering has got two types of riser designs. We will be covering both of them now. Then we have got direct applied risering, which we will be covering later on, followed by the riserless design of the risers. So pressure control risering and bottle risering, directly applied risering and riserless design are the methods used for riser design. Now let's see how we apply each of these methods to design the risers. When the mold is weak, green sand, shell sand, and other molds which we have discussed, and the casting modulus or the significant casting modulus is greater than 4 millimeters. Weak mold and higher modulus. Weak mold with casting modulus more than 4 millimeters, we use the principles of pressure controlled risering. Weak molds and casting modulus greater than 4 millimeters use pressure controlled risering. When the mold is strong and the casting modulus is less than 25 millimeters, or when the mold is weak and the casting modulus is less than 4 millimeters, we use the principles of direct applied risering. So strong mold with less than 25 millimeter modulus, significant modulus, or weak mold with casting modulus less than 4 millimeters, use direct applied risering. When the mold is strong and the casting modulus is greater than 25 millimeters, we use riserless methods. So this gives you a clear picture when you get a new casting drawing. After you apply the machining allowances, the draft angles, and we are ready to design a gating system, that is when you determine the modulus of the casting and you know what method of molding you are going to use. You know the mold is weak or strong. You know the modulus of the casting. So knowing the modulus, mold quality weak or strong, you can decide which principle of risering you have to use to design the riser for your cast. Pressure control risering, directly applied risering. What are the principles of pressure control risering? Let us imagine now you have, after pouring is completed, there is a drop of metal temperature till it reaches a solidification temperature. Whenever the temperature drops of liquid, the liquid contracts. So liquid reduces in volume. So there is the first tendency of the liquid metal after pouring the mold is to contract in the mold till it reaches a solidification temperature. So after pouring is completed, the liquid contracts. The riser should compensate for this liquid contraction. So when the riser feeds metal from the riser into the mold cavity to compensate for a liquid contraction taking place when the metal is cooling in the mold up to the solidification temperature. There is a little space created inside the mold because the metal has gone from the riser into the mold cavity. So there is space created inside the mold, inside the riser, when the cooling of the metal is taking place in the mold. Is that clear? So we have got metal cooling and contracting, and this contraction is fed by the metal in the riser. So some metal from the riser goes to feed the contraction during the cooling of the metal. So there is some volume created in the riser. So riser compensates for the liquid contraction first. Now when the solidification starts, when the expansion starts, the mold deformation is avoided by pressurized liquid from casting feeding back to refill the blind riser. There's some volume created in the casting, in the riser. So when the solidification starts in the casting, the metal will expand because the graphite is having lower density than the liquid iron. So when the graphite is forming, the volume will expand. This volume will put pressure on the mold, and this volume increase will push some liquid metal into the riser where the volume was created by pushing the metal during the cooling process, liquid contraction. So the liquid contraction is fed by the riser. The volume is created inside the riser. Then during the expansion, the metal volume increases, and we tend to push the expanded metal into the riser. So the riser will receive the expanding liquid metal, and the pressure on the mold wall will reduce. We have seen the mold pressure wall can be as much as 2 megapascal. So ideally, riser should refill just before expansion stops. So when the riser refills just before the expansion stops, there's some expansion still to take place. This expansion puts all the remaining liquid at a slight positive pressure. And this slight positive pressure is what prevents secondary shrinkage in the casting. So ideally, the riser should refill just before the expansion of the metal stops in the mold cavity. When the expansion of the metal is still going on and the riser is filled, this remaining metal is put under slight positive pressure. This pressure is enough to prevent the secondary shrinkage defect in formation in the cast. This is the basic principle of pressure controlled risering design. Understand this and you'll be very successful in riser design, and control the processing parameters which increase the tendency of shrinkage in the metal. There are, on the left-hand side is the graph which indicates a curve which has a solid line. That line indicates the average quality of the mold, average metallurgical quality of the mold or of the iron. Above the curve is good metallurgical quality of the iron, and below this line is the poor metallurgical quality of the iron. We have seen what is a good metallurgical quality, and we have seen what is a poor metallurgical quality. When we use this, the Nodutalk method to get approximate cooling rate concept, Nodutalk, if it is around 280 to 300, that metal can be considered to be of good metallurgical quality, and lower Nodutalk can be taken as weak metallurgical quality. So assuming the metal quality is average, you go on this solid line, which is on the y-axis, the significant modulus which you have calculated from the casting. Significant modulus is the highest modulus for which you are designing the riser. So go to the significant modulus and go down on the x-axis, which gives you the riser neck modulus. So casting modulus is significant modulus for the casting, and the riser modulus is the neck modulus. And below the neck modulus, you get the riser modulus, which is 1.2 times the modulus of the riser neck. So you get the significant modulus of the casting. From the significant modulus of the casting, with the help of this graph, you get the neck modulus. Once you get the neck modulus, you can get the riser modulus. Once you get the riser modulus, you are ready for doing the riser design calculations, all the dimensions. On the right-hand side, we have shown 3 types of risers. Type 1 riser has contact in the cope. At the bottom, you see dotted line. There is a riser neck. So in type 1, the riser contact or the neck is in the cope. Cope on the top, drag at the bottom. In type 2, the riser neck is at the bottom in the drag of the mold. So type 1 is riser neck in the cope, type 2 is riser neck in the drag. Or you can have a combination of part of the neck in the cope and part of the neck in the drag. In both these cases, you use type 2. And then you have third, there is a breaker core or is used to give a neck or a notch to feed the metal from the riser, which is a top riser. So you have got three types of risers shown over here. Riser with a cope connection, riser with a drag connection or connection between the cope and the drag, and a top riser. So from these types of riser, you know the geometry of your casting for which you are designing the riser. So you know which type of riser you're going to use. Once you know the type of risers to be used, look at the small table on the right hand side. It gives you the riser diameter based upon the riser modulus. You have calculated the riser modulus from the figure on your left hand side. So from the table riser type 1, you know the riser type, you know the riser modulus, you can determine the riser diameter. So you have got the riser diameter. This is the diameter of the riser at the parting line. So you have got the diameter of the riser at the parting line. Look at the figures. The diameter is shown in the figures. So you got the riser modulus casting significant modulus. From the figure, you got the casting neck modulus, riser modulus, neck modulus, and then the riser modulus is equal to 1.2 times the neck modulus. So you have got all the parameters to give you the riser dimensions. Riser diameter is available. Now, most of us have seen that in steel casting, the riser has got a V-type notch on the top. That is effective in steel casting, but it is not so effective in sand risers used for SG iron. In SG iron, normally we do not provide a notch. We should provide a little dimple, sand dimple in the mold. The sand dimple is given at the top of the riser. These are blind risers, so the dimple is formed by the mold. Look at the mold dimple. If the diameter of the riser at the parting line is D, then the dimple on the top has got a diameter around 0.2 D. From the D, we get the riser diameter at the parting line, and from the D, we get the riser diameter at the top. Top riser diameter is approximately 0.75 diameter. And the other important figure is height to diameter of the riser. The riser height in this pressure control risering system is height is 1.5 times the diameter. Very simple. Height 1.5 the diameter. From the casting modulus, again starting, I'm repeating so that you get it clear. From the casting drawing, we get the casting modulus or the significant modulus. From the figure, depending upon the mold quality, good quality iron, good quality, poor quality iron, or average quality iron, we get the riser neck modulus, and from the riser neck modulus, we can get the riser modulus, or you can take the riser modulus from the figure. Once you got the riser modulus, we can get the riser diameter. The riser diameter at the parting line. From the riser diameter, the height is 1.5 times the riser height. We got the riser height. From the diameter, we know the type of notch, the sand notch to be provided to keep the riser hot. When the sand notch is provided at the top, the sand becomes hot. The sand becomes hot, it keeps the metal hot. When the metal is hot, the atmospheric pressure works on the metal to push the metal into the casting when the metal is required by the casting. I hope this is clear. Now, once you have got the neck of the modulus of the neck, this figure can be used to decide the neck shape. The neck can be either round or square, or they can be rectangular or any other shape. So once you know the riser modulus, riser round or square neck dimension is 4 times the riser modulus. The neck modulus. So the neck can be of square in section or round in section with a size of 4 times the neck modulus. If it's a rectangular neck, we have seen it should be wide and small in height. So the rectangle neck is 3 times the modulus of the neck, which is the height, and 6 times the modulus of the neck, which is the width. So this is a thin neck, the ingot, which will solidify fast immediately after the pouring is over. This graph is normally used to determine the dimensions of the neck. Once you get the modulus of the neck, you can get the dimensions of square, rectangular, or round neck from this dimension. Or you can have any other shape of the neck so long as modulus is as given over here. Now, when you connect the riser to the casting, in this figure, in this graph, look at the figure in the middle. There's a cope, there's a drag. On the right hand side, there's a casting. There's a casting is connected to the riser. The riser diameter is shown as D, and the riser height is above the highest topmost point of the casting. only the part of the riser which is above the topmost part of the casting, which is in this case the shaded area, only that part of the riser which is above the highest point of the casting, which is shown as shaded area over here. This is the only part of the riser which can feed the feed metal into the casting to overcome the shrinkage. So the highest part of the riser should be above the highest part of the casting, and the shaded area will tell you the feed metal that will be feeding the riser. For all riser calculations, I take normally 5% of the poured weight of the metal in the mold, 5% of the poured weight of the metal as the feed metal required for the casting. People talk about 3 to 5%. I normally take 5% to be on the safer side. 5% of the mold liquid metal weight of the mold is the weight of the metal required for feeding the shrinkage in the casting. You can have the once you got the feed metal weight, you can get the feed metal volume from this graph. On the y-axis, you see the feed metal volume. You know the X, you know the riser design. How much is the amount of riser above the highest point of the casting? So that is the X, dimension X. So if you have this dimension X, what is the feed metal volume you're going to get from your riser is determined from this graph, from the figures given on the y-axis. So you know how much metal is available. If the riser volume is feeding less than what is the casting requirement, casting requires 5%. If the riser volume in this shaded area is less than 5%, you have to use more than one riser. Is that clear? If the riser feed metal from the riser is less than the casting metal requirement, feed metal requirement, then you have to use more than one riser. We have seen now only that portion of the riser which is higher than the highest point of the casting to which it is attached will compensate for the liquid contraction in the cast. I've explained to you in details. This is very easy to understand now. The feeding distance should be assumed to be maximum of 10 times the neck modulus. What is the feeding distance? The distance to which the metal from the riser can go into the casting cavity and feed the shrinkage is known as the feeding distance of the riser metal. The feeding distance of the riser is assumed to be maximum of 10 times the riser neck modulus. For this to be effective, gauge should be very thin and must solidify soon after the pouring is complete. We want to isolate the gating system from the other system, which is casting and riser. So casting and riser is one system and gating is the other system. We want to isolate the two. So we use the gauge which are thin and wide so that after the pouring is complete, the gauge solidify and isolate the gating system from the casting riser system. So the riser can absorb the metal volume increase during the cooling of the metal in the mold and can give the metal to the casting when the solidification starts and the graphite expansion takes place. Then it can receive that metal and take all the pressure so that the mold wall is not expanded. So it gives the metal during cooling of the mold. It receives the pressure of the liquid metal, volume of the liquid metal to reduce the pressure on the mold and gives you good dimension casting without mold wall expansion or mold wall movement. So feeding distance should be assumed to be maximum 10 times the modulus of the neck. For this to be effective, this should be very thin and must solidify soon after the pouring is complete. Now we'll talk about the bottle riser. We have completed one design of the riser by the pressure control method. Bottle riser is another design which I prefer as a pressure control method. This figure is not to dimensions. This is just to indicate the important parameters in the bottle riser design which we have to consider during the dimensioning of the riser. At the top, we have got the riser diameter. The riser height is shown on the left-hand side. There is a dotted line, solid line on the two sides dotted line. This is known as the pipe. The volume of this pipe is found out from the height to diameter ratio. Top of the riser has got a diameter. The base diameter is given at the bottom, which is connected to the at the parting line. On the right-hand side is the neck. So the riser above the neck gives you the height of the riser. And the height of the riser is also the height of the pipe in the bottle riser. So the pipe is, how to design the pipe, you will see in the next slide. But just look at the parameters. Base diameter, same as before. Top diameter, we will define. Riser height, we will define. And neck is shown over here. So this is typical bottle riser and shape, which is the shape of a conical bottle, and it is not to scale. Now we'll go and see the scale. So you see in this bottle riser, At the top, we have got the riser top diameter. Then we have the working volume or the volume which feeds the liquid metal to the cast. Then we have got the riser gate on the right hand side, which is thin and wide. Then we have got the riser diameter where the riser is connected to the casting. Next to the riser, we have the neck, riser neck. The riser neck has got a length which is defined over here by providing the radius to the neck so that the riser is knocked down to a smaller size and easy to knock out the riser from the casting in a fettling operation. You have got the edge, which is the height of the riser neck, small edge, height of the riser neck. Radius should be provided so that the sand does not become very hot. Otherwise, there will be shrinkage at the connection. So this gives you the dimensions of the risers based upon the various parameters we have seen in the previous two slides. So use these two slides when you are designing the bottle riser. Now we'll go to the design of the bottle riser. First, you have to decide which is the flask you are going to be using. You have to use the flask which can accommodate the highest, tallest riser. So the flask, we have got limited flask in your foundry. So once you have selected the flask for your casting, for producing the casting, from the flask, you know the height of the flask. So select the riser which will fit the flask with the little amount of extra material on the top where after pouring, the metal will be in the pouring cup. So below the pouring cup is the maximum metal level that will be seen in the coke mold. So the riser should be slightly smaller than that height. So you have to keep the pouring cup as after finishing the pouring, the metal in the pouring cup should be as low as possible, and so the riser will be lower than that level in the mold. So highest riser that can accommodate in the flask after pouring is over should be considered in a riser design when you're designing a bottle riser. So you have got height to diameter ratio of the bottle riser starting from 5:1 on the left hand, on the right hand side, 6:1, 8:1. You can draw your own table also. From this table, once you know the top diameter of the riser, it will give you the feed metal weight in the pipe. So you know the diameter at the top. You know the feed metal weight available from the riser. And this feed metal should be around 5% of the total volume of the metal in the mold. Mold weight, 5% of the iron in the mold is the feed metal requirement. And this 5% feed metal requirement should come from the pipe we have seen in the bottle riser. And the dimension of the pipe is given by the dimension of the top diameter, bottom diameter is the same, and the height of the pipe, which is the height of the riser. Is this clear? Now we'll go through the calculation, very easy. Riser side calculation step by step. The calculations to obtain the dimensions of a conical riser are very easy. First, we find the significant modulus of the casting section to be fed. We have seen that thing. The riser should be able to supply 3 to 4%, but I normally go for 5% to be on the safe side. Riser should be able to supply 3 to 4% feed metal, minimum of 3% of casting weight for a single riser. I take it as 5%. Then determine the feed metal requirement either in pounds or cubic inches through the equation given below. Weight of the feed metal required, volume is available. Once you know the volume, you know the volume of the cylinder, and therefore you know the volume of the pipe, and therefore you know the dimensions of the pipe. First, the calculation is the modulus of the casting, significant modulus of the casting. Then the riser should supply about 5% of the feed metal, and determine the volume of the metal in the pipe, and therefore you go to the riser design. To obtain the calculation to obtain the dimensions of the conical that will be easy. Diameter at the top, determine the top diameter and height based on the feed metal requirement. We have got the feed metal requirement, and therefore we can determine the feed metal top diameter of the pipe and the height of the pipe. Riser height should be more than 4 times the riser diameter to contain the feed metal. This is important. The riser height should be more than the 4 times riser diameter at the parting line to contain the feed metal. A taller riser allows for better piping. See table 8 I gave you earlier, 5:1, 6:1, 8:1. A taller riser allows for better piping. A taller riser allows for better piping. See table 1 for height to diameter ratio at the top. Riser height, feed metal requirement, and weights are available. After you get the neck modulus, you can get the, after you get a riser significant modulus, you got the neck modulus. After you got the neck modulus, you know how to design the neck, round, square, or rectangular necks. 3 times the modulus of the neck multiplied by 3 times the modulus of the neck that 3 times the modulus gives you the height of the neck, and 6 times the modulus gives you the width of the neck. Riser is usually flat on the top and can be either flat or have a drag heel on the bottom to increase the heat in the riser neck area. If the riser is not having the bottom in the drag, then you don't get enough heat in the riser. But I have worked with riser without the bottom, just the whole riser in the cope. The riser is usually flat on the top and can be either flat or have a drag on the bottom. So step by step, you have got a significant modulus of the section of the casting. So riser diameter is equal to 4 times the significant modulus plus the riser diameter at the top. Can we go to the slide on the riser sketch? See, the riser diameter is given by 2 times the modulus on the left-hand side, 2 times the modulus on the right-hand side. So 4 times the modulus plus the riser top diameter. So 4 times the riser modulus plus diameter at the top gives you riser diameter. So riser diameter is 4 times the modulus of the riser plus riser top diameter. Casting feed metal requirement 3 to 5%, average 4%, I use about 5%. Riser feed volume determined by the riser top diameter and height to diameter ratio in the table. Use tallest possible riser for the flask size. Riser height is H by D ratio multiplied by riser top diameter. The risk neck calculation, it's not be risk, it should be riser. The riser neck calculations are done the same way for both risering methods. The riser neck calculations are done the same way for both the risers. All risers should preferably be blind. In SDN, all risers should preferably be. For example, pound plate casting dimensions are given by 10 inch long, 20 inch wide, and 1 inch thick. So modulus is 0.43 from the calculation I gave you earlier. 2 times A into B divided by 2 times A into B minus C. Casting feed metal requirements is a formula we gave you. It comes out to be 1.5 pounds or 6 cubic inches because the density of the metal is 0.25 cubic inches per inch. Riser top diameter 1.2 inches. Riser diameter at the base is 1.2 times the riser top dimension. Riser height is from the table, height to diameter ratio we know. So riser height is 1.5 times, 1.2 times the 5. Riser neck 6 times the modulus of the casting. Riser neck dimensions given, you can calculate the height and the width of the riser rectangular neck. We'll talk about the last riserless design of the conditions. Under what condition can we make the casting without the riser? We have seen the pressure control risers with the riser. We have seen the bottle riser casting with the riser. Now we'll see riserless design. For riserless design, you require high metallurgical quality of the iron. The metal should be of high metallurgical quality. It should be poured into very rigid molds, properly clamped and hard molds. Minimum casting modulus should be 25 millimeters. Temperature for riserless castings should be, pouring temperature should be between 1270 and 1350 degrees centigrade. For fast pouring, you need good venting. So you have to have fast pouring and good venting to release the back pressure of the gases in the mold, which are formed during mold pouring. Variation on the pouring temperature may cause a small depression on the top surface. Some small variation in pouring temperature may cause a small depression on the top surface. Then we can use a small blind riser to feed the liquid contraction metal shrinkage. Small blind riser, very small one. This riser volume should be about 2% of the casting volume. The other places we have seen about 5%. 3 to 5%, and I use 5%. So in the riserless casting, at the most, we may have to use a small riser at the top if there is a small shrinkage of about 2% of the casting volume. But feed the riser volume about 2% of the casting volume. Directly applied risering is the third method of risering we'll be discussing. What are the conditions required? Rigid molds if casting modulus is more than 4 millimeters. Good control of pouring temperature. Whatever the pouring temperature is decided by the casting section. So the pouring temperature will be decided by the casting section, and the pouring temperature will be casting section pouring temperature plus minus. For modulus of less than 4 millimeters, gating system can be used for compensating liquid shrinkage. Riserless casting. So if you have to use small riser, you can use a gating system as a small riser to compensate for the liquid shrinkage. For higher modulus, molds must be rigid to prevent expansion. Gate length should be at least 5 times the gate thickness so that the gate solidifies before expansion begins. We want to isolate the gating system from the casting, and therefore the gauge must isolate the grating system from the cast. These are other aids which we use for making sound castings: exothermic sleeves, insulating sleeves, or bottles, insulating exothermic sleeves, or chills. Chills are normally used of gray iron or silicon carbide or graphite block. Gray iron is the strongest chill. Silicon carbide and graphite blocks have to be replaced. Gray iron also has to be replaced when it begins to crack, or when carbon from the gray iron is all burnt out by using a chill. So when there is no carbon flakes in the chill section, that chill is useless, and therefore you have to change the chill. The chills are used to increase the feeding distance. If the feeding distance of the metal from the riser is 10 times neck modulus, as we have seen, and the casting length is higher than this or longer than this, then we have to put the chill on the other end, so that the chill will solidify the metal and aid in increasing the feeding distance.
So one question what we have received: which factors affecting the metal contraction effectively? How to improve the metal contraction in the pressurized gating system?
What factors in the metal contraction is the factors which increase the shrinkage tendency. I have given you some of the processing parameters which increase the shrinkage tendency. The factors which increase the metal contraction are the factors which increase the shrinkage tendency. The whole idea is, what causes shrinkage? One is not enough metal to feed the shrinkage. It's caused by the metal expansion being lost to the atmosphere or lost to the mold. If during the graphitic ion solidification, the graphite which is coming out occupies more volume, and therefore the liquid metal expands during the solidification process. So, good nodal count will increase the graphite formation, and therefore it will increase the pressure. And when the pressure is increased, the mold will expand. But we don't want the mold to expand, because if the mold expands, there will be shrinkage in the casting. So, to allow the mold not to expand, we push some of the extra metal which has been formed in the casting cavity during the solidification of the liquid metal. When the graphite is coming out, the extra metal we push into the riser, which had already fed the contraction shrinkage when the metal was cooling from the pouring temperature to the solidification temperature. When that volume is available, some of the metal from the casting volume, which expands during the solidification process, goes into the riser. And so riser relieves some of the pressure which is on the mold, which causes mold wall dilation. Once the mold wall dilation is controlled, and towards the end, very little metal left, and that little metal is likely to form secondary shrinkage. Now, to avoid the formation of secondary shrinkage, we put little pressure inside the mold cavity, so that the neck solidifies before the expansion ceases, so that little pressure which is generated inside the mold after the neck freezes feeds the secondary shrinkage. So that's how we avoid the secondary shrinkage.
Now, sir, next question is how to determine the chill dimensions?
Normally, the best way to have a chill dimension determined is to take the chill, and the modulus of the chill should be equal to the modulus of the section which is to be chilled. So you can use the same section modulus, significant section modulus, as the modulus of the chill, if you want to use a chill. Generally, that becomes too big a chill. Best chill is same section modulus as the significant section, and the least is half the section modulus of the significant section. So the chill dimension should be half the significant modulus of the casting section to full significant modulus of the casting section. This is how you design the chill. And the chill should be short blasted after every use. After short blasting, you must remove any pit marks in the chill. If there's any graphite pulling out from the cast iron chills, then you must repolish the surface to remove the pit marks. So short blast the chills, remove the pit marks, and the dimension of the chill is the maximum dimension is the same as the modulus of the casting to which the chill is applied. Minimum should be half the modulus of the section to which the chill is to be connected. Is that right? Is that okay?
When Mr. Nitish Sangol has asked how to improve riser efficiency when casting solidify late. To improve the riser efficiency when casting solidify late, or the cutoff is in earlier in some cases.
So earlier in some cases, then the riser, there will be mold wall movement, because the pressure will not be relieved from the casting. If the pressure is not relieved, then if the mold is a strong mold, there is no problem. If the mold is weak, then the expansion pressure will deform the mold, and there will be mold wall movement, which means the mold will get enlarged, and therefore the casting will get enlarged. And when the casting gets enlarged, you are likely to have shrinkage defect inside the casting.
Yeah, so how to improve the riser efficiency when casting solidifies late?
Yes, so if the casting solidifies late, you have to keep the riser neck open to increase the riser neck.
Increase the dimension of the riser neck, yeah.
Increase the dimension of the riser neck, or get the riser closer to the casting. That means reduce the distance between the riser and the casting, or reduce the length of the riser neck. Just understand the principle of pressure control risering. Once you understand the principle, you will know what is to be done to increase the riser efficiency.